So apparently I'm Marcel and this is Olivia.
Yes, indeed.
Was not hard to guess, right? And I learned that there's a parallel talk which is also pretty popular. So thanks for joining our talk. So we try to make it as interesting as possible. It's a tough topic. We heard about this morning already in the keynote about reinforcement learning, and so hyped and new and exciting and things like this. So, but why did we pick this wonderful image with the hammer and the egg? I usually say at the beginning, what we currently have is this deep learning approach and the CNN stuff, where we have the feeling we have a hammer in our hand and everything we try to solve looks like a nail and we just hit it with our hammer. So every single problem we find right now in AI, so the solution we try to tackle it is using deep learning approaches, say CNNs. Maybe after the talks this afternoon, some try to use RNNs. Doesn't matter, but we would like to introduce something totally new. Well, it's not totally new. Nothing is new in this space at all, right? This is all old stuff. We didn't reinvent the wheel, but we think that it's pretty interesting. So it probably gives a little bit of teaser when you go home and to think about something new. Right? Talk about something old is easy to give some triggers for the evening, for the weekend to work on is actually something that I think, or we think is important. And this is why we have chosen this topic. It's about reinforcement learning. And the reinforcement learning goes sometimes really hand in hand with robots and teach them and learn and stuff like this. So it's a slightly different approach. So try to be open and try to learn something.
So just as a question beforehand, who has already done something with reinforcement learning? Okay. Or who knows about reinforcement learning?
Well, when we ask this question, normally who worked with reinforcement learning, I would say 90% in the audience as well. Yeah, we did it already, so we are expert in reinforcement learning. It's totally unusual to have only, I think, a few of them, but good. Maybe now it's different than the other talks.
Cool, yeah, then let's just get started. Who is a fan of Big Bang Theory? Okay, more people. Yeah, so I'm a huge fan of Big Bang Theory as well. And I think there's like one scene in Big Bang Theory which I find is kind of similar to reinforcement learning as well. So we can see Leonard, Penny, and Sheldon. And Sheldon is trying to train Penny by giving her rewards every time she's doing something good. So every time she's saying something smart, he's like, okay, yeah, that's worth a piece of chocolate. So offering her a piece of chocolate just right here. And we can see that at some point Leonard is like, okay, that's kind of bizarre. Usually Sheldon is not really that nice, especially like at the beginning of the series to Penny. And then yeah, soon figures out like, oh, are you trying to train my girlfriend just like any other dog or cat? Yeah, so that's essentially the idea of reinforcement learning as well. You interact with an agent, or there's interaction between agents and the environment, and there's always this idea or this concept of reward. And based on the reward, certain behavior or certain actions are going to be repeated then later on as well. So yeah, there's a little longer definition with like learning from interaction, but yeah, essentially the interaction between Sheldon and Penny here in this case, and then the reward being the pieces of chocolate. I guess other examples of reinforcement learning can be seen in everyday life, especially like with little kids or a baby starting to walk as well, is trying to interact with the environment, like with the ground, and then also trying to figure out, okay, what actions do I need to do to then be able to still keep my balance, but also walk one step further to the front.
So this statement, by the way, from Sutton and Bartow from Reinforcement Learning, this is actually coming from a book, which is called Reinforcement Learning, an Introduction into Reinforcement Learning, I think it's called, which is the so-called Bible for reinforcement learning. So there are some other books which are probably better than this one, but this is considered to be
the first one being there.
Well, at least the the book which basically coins this reinforcement learning idea pretty nicely.
So let's just take a step back. How does reinforcement learning really fit into the picture with all the other, or with machine learning in general? So there's one class which is usually like the first, or the first class, or the beginner's step into machine learning, which is supervised learning. So yeah, it's about, you usually answer questions like how many, how much. So these are regression or classification problems. The next area is then unsupervised learning, meaning, okay, we don't really know the structure of the data yet. We don't know anything about the data yet. And the question that one would often, that we usually try or tell our customers, the question that you want to answer with unsupervised learning is like, okay, which groups, or how many groups are there? And then the final one being reinforcement learning. So this is learning by trial and error. So we can see a couple of sample questions that you would want to answer with reinforcement learning, and one of them being, should I rise or lower the temperature? And we were having a discussion beforehand as well, and then also a kind of nice link to the keynote earlier today when it was regarding the energy, or the energy consumption, or the cost that you have to spend on cooling your data centers as well. So what action do you have to do to, or conduct, to keep a certain temperature? And Marcel is going to have a more in-depth example on reinforcement learning and on cooling as well, or on AC in general. There are quite a few examples or applications of reinforcement learning out there already. Just to pick some of them out, the first one being like a fly stunts of helicopters. So there's this video conducted by researchers at Stanford University where there's a helicopter. I think it's a mini helicopter. Yeah.
Right. Yeah.
And this one is pretty much doing like some flying stunts and doing those saltos, which is pretty amazing. But yeah, this is only being done using reinforcement learning.
So the tricky part is that this helicopter is doing really maneuvers where he's flying upside down, or where it's doing some weird behaviors in the air, which is hard to basically control with a remote control. And they basically came up with a system based on reinforcement learning. So they didn't do the learning on the physical system, right? It would crash quite a lot of helicopters.
That could prove quite expensive. Yeah.
Right. So they simulated it, and at the end they had kind of a model, and then they were installing it to control the helicopters. And it's really quite impressive what kind of maneuvers this helicopter can do just by learning it based on reinforcement learning.
Another example is the last one that is written there with chatbots. So bots are all the hype at the moment, or especially with Microsoft or our customers, almost all of them always want to have a chatbot. And there you could also use the response of the user as implicit feedback or implicit reward as well. So when I ask a question and then I get a response from the chatbot, and then I ask like, what the heck are you talking about? Like, I actually meant blah, blah, blah. So this is definitely a reward which says like, okay, the chatbot didn't answer the question at all that I asked. So why is reinforcement learning so different to supervised or unsupervised learning? So the first one being, okay, reinforcement learning doesn't have a supervisor, hence that picture of a supervising animal. So it only has a reward signal. And the thing is, we can, or through the reward signal, we can judge whether it has been a good action or a bad action, but we can't really say from that whether that action has been the best action out of all the options as well. The other thing is that the feedback is delayed and not instantaneous. So it might be possible that the reward is not coming straight away, but only like a few time steps much later, where we see then that, okay, we bumped into, or we got trapped into some local maximum, and therefore need to, approached it in a greedy way, and can see that the reward or the more global reward actually isn't that positive as we would have expected beforehand. And then the third point is agents' actions affect the subsequent data it receives. So obviously the way that a robot is moving around or navigating itself through a room has a clear influence on what signals or what rewards it gets, also what it observes. Because obviously all the observations from that point are different to like all the observations from that point. And therefore those actions may have long-term consequences. So let's have a closer look at the reinforcement learning framework. So two main components, which is the agent, so that robot, for instance, that is moving around, and the environment, meaning the environment of the robot itself. And those two components interact with each other in various ways. So the first one being the agent executes a certain action. So a robot is moving one step further or one step to the left, or a joystick is being moved to the front or to the back. And from that action, it then receives some observation. Observation meaning, okay, this then, I can see a completely different surrounding given by the environment. And it also receives some scalar reward. So I've mentioned rewards before and quite a lot of times already. So thinking back of the Penny Sheldon situation, the reward was, okay, we get one chocolate. So it's fairly binary. One key point here is that the reward should be scalar. So it could be binary, but it shouldn't really be two-dimensional. So one example could be, I need to decide what really my goal in that scenario is. So looking into like the work environment, do I travel once again to the US to make my customer happy, or do I stay home just to keep my boyfriend happy? And there I need to make sure I can take those two components and make a scalar out of that, and weigh which one of those two components is more important than the other. And then on the other hand, the environment receiving the action, emitting an observation, and also emitting a scalar reward. There are two approaches here, just for completion's sake. MDP meaning Markov decision process, POMDP meaning partially observable Markov decision process. So the difference between those two approaches is the current state dependent on, or is the future state dependent on just the current state or on the history of all the states beforehand? This is the main difference between, the MDP meaning, so the state is, or Markov decision process meaning that the state, the future state is only dependent on the current state, and all the historical states or all the past states beforehand are not, or do not actually have any influence on the future state. Here we can also, to dig a little deeper into that, so we see one more thing, meaning the policy. So the policy says what the probability is that the agent's action will be A. So there can be a multitude of actions that an agent can do, and therefore, the policy tells you what the probability is that the agent is conducting a certain action. And then as soon as you always go through that loop, you always transition from state ST to ST+1, pretty much.
I think this is my slide, but anyway, let me just add one thing. Well, because in the upcoming slides, we probably might mix terms a bit. So it's all about terms, and it's all about very simplistic ideas here, right? Olivia said already, we have an agent, we have an environment, then we have an action, then we basically have a reward, which we receive from the environment or from someone, and we probably have observations of the environment. What we see in history is that we usually have observations, reward, actions. This is either in sequence, ideally it is. It's always like this sequence, right? Observation, reward, action, blah, blah, blah. And then we can build a state out of it. And basically the state, what you build is the agent is trying to build either a state of the environment. So what is this environment in, which kind of state? And you can see the state is basically a function over the history data, like observations, rewards, actions, and so on and so forth. It could be whatever kind of functions, and here it gets really fuzzy, I have to say. And if we are able, instead of keeping all the states in the history, to accumulate everything in just the last state, in one single state, then this is what Olivia was saying, it's a Markov property actually, and it's just enough to measure and to observe only this state, this final state, to trigger basically the next action. And this is what Olivia was saying. There's a policy which basically says, well, the next action based on my current state is blah. And then you trigger action blah, change the environment, have another observation, recalculate your state, trigger another action based on the policy, what you have observed so far. This is all what reinforcement learning is basically about. You have an agent, you have an environment, you have states, you have actions, and rewards. That's it. Can you quickly click? And this is basically what this summarizes. And at the end of the day, and this is finally what you want to achieve when you have all this together, actions, agents, rewards, is to maximize the reward. Yeah, this is a goal, to maximize the reward. The goal is not, well, the goal is an implicit goal, but we would never tell the agent, find the exit of the maze. You just say, run robot, and the robot is doing things, is collecting rewards, it's failing, then collecting the reward, start again, and at the end, whatever maximizes his reward is what he should have achieved. So you have to make sure that you build a reward system so that finally it reaches the exit of a maze, if this is a goal, if this is your goal. But you just give rewards, like a chocolate to Penny. There's no final goal there. It's just to make Penny a smarter person. I don't know if this is required, anyhow necessary or not. Can you click again? Okay, just to keep you a bit busy, there is a small experiment we would like to conduct with you. Okay, yeah, thanks. So you are now, guess who you are on this picture. Right, you are the rats. And we are doing an experiment with you. So at the end of each of these rows, you receive a reward. So you as a rat, you see there is some light blinking, another light blinking, then you pull the lever, then you hear a bell ringing, and then you get an electroshock. Next time, there's a bell ringing, a light flashes, you pull the lever, you pull it again, and you get your chocolate or hamburger, whatever you prefer. So last one is, pull the lever, some light is flashing, you pull the lever again, bell is ringing. What is your reward? Any guesses in the room? Electroshock. Who likes who likes electroshocks? Me. No, who thinks it's electroshock? Okay, who thinks it's a hamburger, praline, whatever you like? Okay, why is it the electroshock?
Based on the last 3 items.
Okay, yeah, cool.
It's arguable either way.
So what, the chocolate guys or hamburger, well, why do you think it's a positive reward you would receive?
Just one light.
Good one. Well, it could be, but it could also be 2 lever pulls, right? Which gives you a chocolate. That is not true or false here, right? You cannot really predict based on this information. It is how you would basically accumulate this final state and how this plays together with reward. This is not a state, right? The state is what you basically build out of this information you had before. So it's not easy to build a state, actually. This is a tricky part. So simple the full reinforcement learning cycle looks, agent, reward, environment, blah, action. All the complexity is inside building a state, building a proper reward system. The action is not so difficult. Sometimes even the reward is easy. The reward could be electroshock or or a hamburger, or it could be success or not success. Okay. Another demo to keep your brain busy. This is, I call it the hello world for reinforcement learning. It's the n-armed bandit problem. Actually, the n stands for any natural number. Let's say we have n slot machines, yeah? This is what a one-armed bandit is, a slot machine. And you have 10 of them. Now, usually they're not giving you all the same reward. So they have some distribution in terms of success and unsuccess. And what you try to do is to try to find out from which one you benefit the most. So which one gives you the most money out, basically. Yeah, this is a typical thing which you could solve with reinforcement learning. So how would you do it? It's pretty easy, right? So you have actually, so this is basically here you see a distribution of rewards a bandit, or how good or bad each bandit works. The higher the number, the better it is for you. The lower the number, it's less good for you. So in this case, basically this guy here, which is 10, 9, 8, 7, 6, which is number 6. No, number 4 is even better, right? Number 4 is the best one. You try to find out number 4, because this gives you the most money back. And in this case, actually, the reward and the observation is the same. You use the rewards as an observation of the system. And what you do is basically you start with an empty set of values, which is basically zeros. You say, from what I know by now is I start with all these n slot machines are the same and behave the same. And they give me the same return, which is nothing at the end. And then you start randomly picking one of these arms. So it might be bandit number 6. So you pull the arm of bandit number 6, and it gives you some return. And the return is basically based on its internal return function and efficiency. So it gives you the .667, and you put it on this, in this vector on the position of this arm number 6. And then basically what you do is now you pick the one which has a maximum number in this row, which is now number 6, and you pull it again. Because from what you know by the first time step, this must be the best thing on Earth, for sure. You pull it again, and it gives you now back something different, right? It will not give you always back this .67, it will give you something negative in this sense. So you build the average and put it in here. So apparently it's not the best on Earth. What you do now, you pick something else, except the number 6, because this is the worst thing on Earth. So now you start with number 2. You pull number 2, it gives you back a minus 1.9 or whatever. And you continue, right? You see where it goes. And at the end, you get a curve, if you average the values, which basically converts towards the maximum number of 1.8, somewhere here, right? This is the maximum number here. And at the end, when it converges and the error is below a certain threshold, then you can check, and you just pick the arm which has the highest number in your vector, and this is the arm which gives you the most reward. This is the n-armed bandit problem. Let me quickly switch over.
Just do a skip.
Okay. Just a bit of code. So it's pretty easy. This one is in Python, but you can make it up in whatever kind of programming language you like. So the bandit itself, it's pretty simple. It has just an action function. So you instantiate it with n arms, in this case with 10. You distribute randomly, fill in the numbers, and then whenever you pick one of these arms as an action, you give back, based on this number at this position, another random value. So this is just simulating my bandit, right? And now I would just scroll this way, but I cannot. So, and then you can build up a greedy function, basically. You pick possible actions, which is basically, as I explained, a 0 from the list, and you start and do things. And when I run this thing, I get this. So here I have, again, 10 bandits, or 10 arms. I run 5 steps, and I get back. So this is my original distribution of the bandits. Here's a sequence of actions. I pull the lever, 8, 9, 0, 0, 0. And basically, this is a reward return, and I fill basically my matrix up with these kind of numbers. So I put in on position 8, this minus 1, 1, minus 8, 8, and then I pull the 0, and I continue pulling the 0, because I think it's the best one, up to here. I could now continue. But what can happen? Actually, what can happen is something like this. So let's assume we have here 10 different arms, and this is kind of the distribution. I probably might end up somewhere here. Right? I think, well, it's a 2, it's a 2, it's arm number 2, it's arm number 2, it's arm number 2. And I will not move out of it anymore. It's kind of a local maximum I'm hitting here. So I try to find the global maximum, which is more on the 8 or wherever. So what I do now, I add some randomness in there to randomly pick a different one. Even if I think it's a 2, it's a 2, it's a 2, maybe I should try the 6. Then I pick the 6. Oh no, it's a 2, it's a 2, it's a 2. Or maybe I should try to pick the 8. Then I pick the 8, and then, oh, the 8 is even better than the 2. Then I continue picking the 2, and I randomly try to find the other local maximum. But I converge at the end. It takes a bit longer, but the conversion rate is much better. So I can run it, and I can compare. This epsilon is basically a gap which decides when I should do a random pick and when I should not do a random pick. So when it's low, the chance that I do a random pick is almost going towards 0. You see it still converge, but not as perfect as a real one. This apparently converges towards a local minimum, and this one towards a global maximum. Depends on how you look at it, right? So this is actually what the n-arm bandit problem is about. Why is this useful? It's useful actually, for example, when you try to figure out what a customer likes. What is his preference? So he's looking for a Jaguar. What does he mean? The car or the animal? So you probably give him the animal, pictures of the animal, for example, and at the bottom maybe some pictures of the car. So, okay, I like the car. I pick the car. So this goes back, as in the n-arm bandit problem, as a reward back, right? And then you basically, the next time you pick the car, you fill up more cars and less animals. And now you basically try to derive and figure out what he really likes. So it's a very simplistic example with Jaguars only, but you can make it more complex easily on different types he likes. So this is how you basically receive feedback and reinforce your system to think and to adapt to the customer's choice. The same as for the bot part. Well, if he replies badly, then it's most likely not the correct answer. You should try something else. But how does a bot knows which one is a better answer? So he just randomly picks something different. Then again, you reply, oh, this sucks. Come on, your answer was not the best one. You pick another one. And then you adapt and you basically converge towards the correct answer. Yes, it can take time. And probably you don't have that much time by talking to your customers, giving wrong answers. So this is why you usually start not from scratch with these models or not with a customer in the first place. You probably build up your knowledge base first and then increase the learning on top of a baseline. Okay, here's another example. Well, we were talking about robots, or we should talk about robots. And this is a bit of an academic example. So there is this Mindstorm robot, and it should find its way out. And I think the way out is somewhere on top left here. And you see it has different states, it has different actions, and it has several rewards. And now you start. And you never tell this robot, find the exit. It's just by collecting the reward and by optimizing this reward in the long run. It's supposed to be a video, but I'm not going to show this video here. We have another one which is even better. But you can go there, visit this, and see. It basically goes and learns. I don't want to talk too much about this one. Today I already skipped a lot of math in the other talk. Here we do the same. Again, it's a reinforcement surface we are scratching here. Yeah? There is so much more in terms of how to calculate the value function, how to calculate the best value function, how to calculate the model-based value function, and so on and so forth. So there's a lot of math. So just to give you an impression, so when you have a policy-based reinforcement, it basically just decides on each of these elements in the maze what is the next action. Go up, go left, go right. It's not more. When you have, there is also the approach of having a value-based reinforcement learning. So when you don't have a policy itself, but you can basically distribute values in your maze, then you try to optimize it based on values. The model one is you try to come up with a model of your environment and build it this way. Different approaches, different ways to solve it, depends on what kind of information you have and which kind of information you don't have. I think I have to skip this one, otherwise we are running out of time. Yeah. Okay, so just to mention it. So it's about cooling the room, like in the air conditioner in this room, make it lower the temperature, rise the temperature, and you can build a reinforcement learning system just by these elements. You have a cooler switch, which you can switch on and off, so these are just your actions you have, on and off. You have your environment, which is basically the temperature you can observe. You could bring in people in there and so on and so forth, but it doesn't matter. The observation is the temperature, and the reward might be good and bad. And then you can start doing things. And you don't tell this agent what he should do. So he just measures 20 degrees, and by randomness he decides, okay, let's switch on the air condition. And after 10 minutes, so it takes some time, it measures the temperature. Maybe it's then 12 degrees, whatever. And then you start filling in these things. So you had the opportunity at 20 degrees with the action on to end up on these temperatures, but you ended up on this one. So you fill in opportunities with one for all these values, and the observation was just on 12 degrees. You could do it the same way if you don't turn it on, you turn it off. You do it the same way. And you repeat this several times, so you fill up your model. And at the end, when there's someone, so far you haven't told the system what to do, right? Now someone says, oh, room, please make the temperature to 18 degrees. And now the system knows exactly what to do. It just goes here, compares the values, so I should achieve 18 degrees, currently I have 20 degrees, I compare the probabilities, so I turn the air condition on. And you never told the system what to do when. There's no rule at all. It's just based on rewards and actions. Yeah, you can imagine. So you have to have several runs here to get to this situation. There are other examples, right, Olivia?
Yes, indeed. Yeah, we are starting to wrap up the session now with a couple of more applications. So there are quite a lot of applications of reinforcement learning done by DeepMind. I'm sure some of you have seen the video or the videos of DeepMind applying reinforcement learning to Atari games. Here it is like one example. It's called Ping or Pong.
Pong, oder?
Pong.
Pong.
Yeah, and the thing is like, so we can easily see that there's this picture with which are full of binary pixels, which is the environment here in this case, and then the agent being, okay, we want to actually control that board that is moving up or down. And therefore the actions are either moving the joystick up or down in this case. Here the interesting thing is it's not just reinforcement learning, it also involves some other deep learning, so yeah, the other hype. Here in this case it's using CNNs to understand what actually is going on in that picture itself. This is one example, and then another one, obviously, as from being from Microsoft, there needs to be something from Microsoft itself. There's a project called Project Malmö from Microsoft Research.
Who in the room knows Minecraft?
Yeah.
Who plays Minecraft? Well, it's less people. Yeah.
Maybe your kids play Minecraft.
Who has kids who play Minecraft? Oh, still not much. Many?
Well, so here the idea is, I mean, thinking back to the fly stunts of the helicopter, you don't really want to have a real-life, well, miniature helicopter and try out all those stunts because, yeah, it might actually end up being really expensive. So you want to have some simulation world. So here in this case, you could use Project Malmö, which essentially is a plugin or like a proxy to Minecraft. So what you could do is you could create your simulation or your environment in Minecraft, and then try out or build your reinforcement learning in whatever language. So like could be Python, Lua, C#, and so on and so forth. And then could see how it actually plays out in that simulation world. We could show you a video as well. To be honest, it's not really, or that video isn't really encouraging because it's that human person within Minecraft that tries to figure out a way through a volcanic area. But it takes an incredibly huge amount of tries to keep on actually falling into the lava itself. So it's like, oh yeah, it's so stupid. Why can I not figure out like how to actually navigate through the volcano?
So we have decided to pick another video which we believe is even more impressive. So we just switch over to YouTube. So what these guys are trying to do is try to have a robot arm doing some movement, which I cannot do. It's about turning a pancake in a pan by just doing this fancy whatever kind of
The
thing.
flip.
So here basically he starts to show the robot arm kind of the search field, to reduce and to constrain the actions he should search. Otherwise it would just take very long. And then basically this arm starts. So now so who can basically do this movement with a pen and a pancake? Yeah.
Okay, quite a few.
And all the who were laughing? So 10 trials. So do you think you are able to do it after 10 trials? Maybe.
Well, Marcel can't.
And Olivia cannot cook. No, I'm kidding. 15, 20. Wait, it doesn't take that long. It looks like in a slapstick, like Jerry Lewis thing or whatever. Okay, now it got it. After 50 trials only, they had the robot arm doing this movement. So imagine you would have to program it to do it. So I'm not a programmer doing this robot programming, but I would guess you would not get it in the first place correctly. So you probably would also have even 50 trials by coding things, getting parameters correctly and things like this to do it. So here it's just by reinforcement learning to get it on this level. So time to wrap up, probably?
Yes. So yeah, we are of the opinion that reinforcement learning will be the next star in the machine learning space. It does have some perks, actually some burdens, let's put it this way. One thing is it is extremely data hungry. So deep learning already requires a lot of data, but also Andrew Ng, I think, mentioned in one of his talks at NIPS probably, where he said like, yeah, reinforcement learning is just like another level of how much data one really needs. I guess in that sense, it's more about like having to go through a lot of simulations to gather that data so that you can really build a good reinforcement learning model. But essentially, it always depends on how complex that problem really is. The other thing is obviously you need a lot of compute power. We see that there is going to be a lot of applications of reinforcement learning in the IoT space, but especially in autonomous driving. So yeah, to learn from the environment how to interact with the environment and getting some rewards. But obviously, again, this is not
cyclist,
something.
hit this pedestrian.
Yeah.
Yes, reward 1,000.
This is definitely something that you wouldn't want to try out in real life. Hence, a simulation world would be suitable or appropriate. We see that there is some good foundation research already and some convincing prototypes, just like the pancake flipping thing. I mean, obviously we need this in the world. But yeah, so in case you, or what we definitely would recommend is there's a YouTube series by David Silver, who is working at DeepMind, and he has done a really nice lecture series here at UCL, I think, on reinforcement learning. And he also is of the opinion like the combination of both reinforcement learning and deep learning is really the AI that
I disagree with you. I don't encourage you to watch the video on YouTube. I encourage you to read the books. So the first one I mentioned, Sutton and Bartow. This one I like much more than this one, actually. If you like math and have it really reduced to just math and algorithms, then this one is a place you want to go. Saying this, so you see we still have some reinforcement learning, so I will offer you some chocolate afterwards for some of your statements, and for some I have to give you some electron.
we have it on video.
Again, thanks. That's for today. Questions?